Hi, I'm Sharad Malik. I'm a professor in the Department of Electrical Engineering at Princeton University. The research in my group is looking at developing methods for designing future computing systems. And the big challenge in these systems right now is how do we make them secure as well as correct? So let's address the security concerns first. We are all aware of cybercrime around us. There are several recent studies which have pointed out the extent of these losses. As a result of this, what's happening is that increasingly security critical functions are moving to hardware. The rationale for this is that defenses implemented in hardware are harder to evade, but the downside is that vulnerabilities, once they are found in hardware, are much harder to patch. So the research questions my group is addressing are, what are the defenses that we can provide in hardware? How do we check them to make sure that these are correct? And then how do we also check that there are no other vulnerabilities that are left undetected? Very related to this are the correctness concerns. Increasingly, getting systems to be correct is the limiting factor in system design. The graph on the top right shows that system verification time is now dominating total design time. And the related graph at the bottom shows that as a result of this, most projects miss their deadlines. And it's not surprising then that often design features do not get turned on because systems have to be shipped at some point. And they're not turned on because they can't be fully verified. So this is obviously extremely limiting. My group approaches both the security concerns and the verification correctness concerns using foundational techniques that are based on mathematical modeling and analysis. In a past project, what we have done is shown how both the systems of interest, that's F here, as well as the properties of interest, that's P here, can be modeled as Boolean formulas. These formulas can then be analyzed to make sure that these properties hold for these systems, and when they don't hold, we can diagnose to see what exactly was the problem in these systems. As part of this, we've developed fundamental algorithms for the basic problem of solving Boolean satisfiability, as well as the related problem of max satisfiability. This work has now been widely used in industry. It's used in systems at scale and has received several recognitions for the contributions that it has made. In more recent work, what we have done is developed mathematical models that take the notion of instruction set architectures for general processors and generalize this to arbitrary hardware. This model, referred to as instruction level abstractions or ILA, just like the ISA, going upwards serves as an abstraction. That is, it tells us what is the view of this hardware as seen by the other components in the system, both software as well as hardware, and therefore can be used to verify the interactions with these other components. Going downwards, again, like the ISA, it serves as a specification for the hardware and something that the hardware implementation can then be verified against. This work is not done in isolation. We work very collaboratively, both within Princeton as well as groups outside. We have active collaborations going on with research groups at Intel and Amazon, as well as with groups at Stanford and Michigan on larger projects. So to summarize, the overarching goal of the research in my group is to help define the next generation of hardware security and verification solutions, and very importantly, make sure that these are actually deployed at scale in industrial solutions. Thank you.